Hello, I am Luca Antiga, CTO at Lightning AI. Today I'll be talking about scaling foundation models with Lightning. So what are foundation models? A foundation model, according to Wikipedia, is a large model trained on a vast quantity of unlabeled data at scale, usually via self-supervised learning. That results in a model that has particular ability to be adapted zero-shot, few-shot, to a wide range of downstream tasks. And what sticks out here is the scale portion of it. So we see that emergent abilities exhibit themselves at scale, at particular scale. So scale is an essential factor in having these very powerful models at our disposal. And PyTorch Lightning has been used often to train very large-scale models. The most famous of them, I guess, is Stable Diffusion itself. So both in the original Convis repo and in the more recent Stability AI repo for Stable Diffusion 2.0, PyTorch Lightning was employed for training the model at scale. And some derivatives of the same model use PyTorch Lightning under the hood, like the more recent instruct pix to pix, where you can change and do image-to-image transformations based on a textual description. And this has gained some popularity recently. But it's not only on the creative side that PyTorch Lightning is widely used. It has a widespread use in science. In general, one of the most famous recent models is OpenFold, which is the replication of AlphaFold 2, which was initially trained on a Google stack. And OpenFold is a reimplementation and a full end-to-end training reproduction of that model that has been published recently, and it uses PyTorch Lightning under the hood. And other frameworks that deal with very large models, just like NeMo Megatron, are powered by PyTorch Lightning, and NeMo itself. NeMo is a set of models that range from acoustic decoders, language BERT, speech synthesis, and vision encoders. And all these different types of models are powered by a system of classes that are based on the Lightning module, so you can train models at scale using the best practices. And NeMo Megatron is one of them, which deals with it's a port of Megatron language model to the NeMo framework. And there are many other examples of projects using Lightning. There are many thousands of them around. Many companies use Lightning, and essentially with Lightning you can focus on the science, and we do the engineering. Although, as we will see in this presentation, there are some particular traits of models at very large scales that forced us to take a step forward. And this is what I've been announcing in this presentation. So let's first take a look at PyTorch Lightning itself. This is the most basic example that you find on the documentation. It shows an autoencoder with an encoder and decoder, two different modules that are depicted at the top. And then you have a Lightning module, which is derived from a Torch and N module. But it's kind of a self-contained description of what the training step will be, what the optimizers that you can use are. And there are a long list of hooks you can implement. So it's really organized PyTorch in the sense that with raw PyTorch, you write all these pieces together in a single script, or you give it the shape you want. With PyTorch Lightning, in particular the Lightning module, this will enforce some structure to your code, but this will allow the trainer, which we see at the bottom, to leverage this structuredness so that you can you can leverage the trainer to implement distributed training strategies and so on, because it knows what to call when and what's your intention within the code. And part of the popularity of PyTorch Lightning is also the fact that beyond decoupling the science and the engineering, where the engineering is represented by the trainer, it also gives an opportunity for teams to collaborate together, because it's immediately obvious what a certain piece of code will do when I look at it, even if somebody else wrote it. So the fact that it's highly opinionated might not be liked by people who want full control and freedom, but it's actually a good thing when you work in a team. And this is the various ways in which you can configure the trainer. The trainer has many flags that you can access to. The more immediate ones being the ones that I'm showing here. You can set the number of devices. You can set the accelerator types. We support a lot of accelerators like GPUs, TPUs, and other accelerators, and then distributed strategies that kind of contain the way the model needs to be distributed across machines, across nodes to do distributed training. And here I mentioned some of the most popular strategies like deep speed, colossal, FSDP, or the standard DDP. And we have other things like callbacks that we see at the bottom of this snippet, where you provide a set of callbacks. The callbacks themselves hook themselves into lifecycle events. And so you can make something happen, even though your original code for the Lightning module doesn't contain this functionality. So you keep your model code clean and in a way immortal, because it doesn't need to change. And then you tweak the behavior, the distribution, what happens during training and so on. Like, do I want to average the weights in the last epoch, for example, or do I want to log certain things at certain points in time, or do early stopping and so on. And all these behaviors can be specified by just passing things to the trainer while not modifying my original code. What happens when you call trainer fit? This is a very high level view of what happens. And you can see here in the first function fit, you do some preparation, and then with each device, you will train the device on the model. And that training on device on the model includes configuring optimizers, and which means instantiating the optimizers themselves. And then there is a for loop across the epochs that will call a function, and that will do one training step at a time, compute the backward, do the optimization step, and so on. And in between these fundamental operations, you have hooks that are called that you can override either in a callback, or you can override them in the Lightning module. And so you can customize what happens through your code. Of course, the price to pay here is that for this kind of convenience is that you need to know what happens. You need to learn what the hooks are and so on. Once you know that, though, it becomes really easy to write training code that will scale a lot. And so to get you to the foundation kind of scale. So from a very high level, this is what PyTorch Lightning looks like. You have a trainer that handles the loop, so it kind of takes your control away from you when it comes to the train loop. And then we have, of course, other loops like validation, test, and predict. But it all works the same. And then you will provide it a Lightning module, which is the model that contains all this steps and configure optimizer or lifecycle events that you want to override to make something happen specifically. You can provide an accelerator, callbacks, we mentioned them, model checkpoint, early stopping, and a bunch of others. And then what strategy do I want to run with? So for example, the deep speed strategy will actually go into your Lightning module and kind of mess with it, replace a few portions of it so it can operate with the strategies that deep speed brings in. So you will do kind of surgery on your Lightning module to enable your model without code modifications to run at a very large scale. So on one hand, with the Lightning module, this is where you operate typically, and it brings you flexibility, the ability to collaborate between people, and to have a really self-contained representation of your model. including the optimizers and the data loading and so on. And then you have boilerplate that you normally have in kind of raw PyTorch that is abstracted away and that is taken care of by the trainer. And so to reiterate, you can focus on the science and we do the engineering. And you can scale up without necessarily knowing the nitty-gritty details of what it means to scale across machines, to have different types of parallelism, including pipeline parallelism, tensor parallelism, and so on, depending on the strategy you pick. And we have extensive documentation on this. However, in the age of foundation models, sometimes the science is the engineering itself. Let's say we come from a period of time where most of the work of a researcher was iterating quickly on the Lightning module, essentially. So iterating quickly on changing the model, experimenting with different kinds of models, ways of loading the data and so on, or what kind of optimizer you were using. And the training code were kind of factored out from the equation. Right now, with very large models and very long projects where I have my giant GPT model with very custom layers that may contain collective operations within the layer to implement certain kind of tensor parallelism. One example is the Megatron LM repo, where this happens all over the place. And the need of like fitting a lot of compute and a lot of data in optimally on machines and so on forces you, for the sheer scale, to want to have a bit more control. And so sometimes the trainer gets in the way, in the sense that it being very opinionated, it doesn't allow you to have full control of what happens during your train loop. And so it was a binary choice until today, where you went raw PyTorch for full control and a bit more boilerplate. But if you know what you're doing, this is great. Or PyTorch Lightning, which, if you know what you're doing, is great if you don't care about what happens in the trainer. But sometimes you do care a lot by what happens in the trainer. So it's a fully managed from a training loop perspective. It's less boilerplate, and boilerplate means code that you don't necessarily fully understand sometimes as a practitioner. So you want it to be handled for you, but sometimes you really want to have control over it if you know what you're doing again. And so we're introducing a new piece of the Lightning framework, which is called Fabric. And Fabric creates a gradient between raw PyTorch and the fully managed experience in PyTorch Lightning. And in the remaining minutes, I'll walk you through what Fabric is and how it can be used in this context. So Fabric, some of you that may know about Lightning Light, it was a precursor of Fabric. So if you know what Lightning Light was, you will recognize a lot of things that characterize Fabric today. But Fabric has been expanded, and it creates this gradient between raw PyTorch and PyTorch Lightning thanks to the evolution that it had over these recent few months. So in order to use Fabric, you configure a Fabric object. You create a Fabric object in the line that says 1. And then you set up your model, optimizer, and data loaders within the Fabric object. And so by passing, for example, a strategy, and we'll see in a second, to the Fabric object, and then call it setup, then Fabric will have the opportunity to modify or instantiate a few things within your model, take the model and optimizer together, and make a certain training strategy work in the future. But then after that is done, then your code will be a modified code compared to your training loop. So you have full control of your training loop, except that you will be able to call a few things on the Fabric object that we'll see in a second that will allow you to still write very raw code, but with full control of what happens. And this is conceptually, if we remember what we said, what we saw for PyTorch Lightning before for the trainer, this is what conceptually Fabric looks like. You have your own training loop. You can call a few methods, and just the API is very small. For Fabric will handle your backward, will handle your logs, and will handle your checkpointing. Of course, these are opt-in. You can also not use this. But if you use them, then you gain some superpower and some boilerplate will go away. For example, the fact that if you log fabric.log and you pass a logger to Fabric when you construct the Fabric object, then that log will go through the logger that you set. And again, you have this advantage where your code doesn't need to be if-cased in 50 different kind of ways in order to support things that you will later decide if you go from your laptop to a cluster, you won't have to touch your code anymore for certain aspects like logging. It supports accelerators, so you don't have manual management of accelerators, just like in Lightning, and the strategy as well. So you will be able to run on multiple machines using deep speed at various stages. With Fabric, with that deep speed specific pieces factored out. And of course, this is your choice. You can also not do that. So it's less opinionated than the trainer. So this is the way you instantiate the Fabric object. You can pass a number of devices, the accelerator types, the strategy, it's a string. It can be an object if you want to configure it. And the precision, in this case, 16 means mixed precision. And same thing with the logger. You can have multiple loggers. And once you provide the list of loggers to the Fabric object, then whenever you call Fabric log, this will log to the loggers you instantiated. Checkpointing is not hard on a single node, single machine. It gets harder when you go distributed, so Fabric will be there to help. You can save a checkpoint that contains whatever you want in this case. So you will just be able to create a dictionary with information you want to checkpoint at some point of your training loop, and then just save it and then restore it. And all the barriers and the operations that collect information through a cluster of machines that are collaborating in this training will be taken care of for you. You can also restore a part of the checkpoint. So if you're only interested in a certain model of a set of models, you can just restore that by creating a dictionary that only contains that key that will then be materialized when you load. So going back to the concept of the gradient between raw PyTorch and PyTorch Lightning, we create a first point along this gradient, which we call it's not an official name, but raw Fabric, in the sense that it's really close to raw PyTorch. You have your code structure the way you want. You don't have to create a Lightning module, for example. You can just use your code for your NN module, whatever you have. But then through the Fabric object, there's some boilerplate that it's taken away from you, and maybe you're not a distributed training expert. So setting up environment variables, managing groups of machines and so on is something that you don't really know how to do, or you don't want to deal with. And so you can get a great advantage from Fabric, as well as these other things that we saw, like checkpointing and so on. And this is the picture we already saw. There's another level you can go to now in this gradient between raw PyTorch and PyTorch Lightning, which is you can use Fabric with the Lightning module. So if you want to still structure your code using the Lightning module, just like Stable Diffusion did, for example, then you can still do it. There's nothing preventing you to do that. I was talking to a company that has adopted Lightning, and they were saying the Lightning module makes it easier for us to hire because people are happy creating models this way. They come maybe from research, from university. They learn how to do it. So they see it favorably that they will contribute and collaborate on Lightning modules and so on. because they see the value of it. So you may want to adopt it for your organization. That's fine. And you can still use it in Fabric, and we'll see an example of that. And if you want to go like a bit more managed, now you can also use the callbacks. So we introduced the use of callbacks in Fabric, where you may want to have a model checkpoint, early stopping, or whatever callback. Not 100% of the callbacks that are working on trainer will work on Fabric, but we're extending the reach of those. And so this will be a bit more managed experience, but you will still have full control on when the methods, the lifecycle methods on the Lightning module, so-called hooks, will be called. So you need to call them manually in the right order because you're in control. The same things for callbacks. You will register lifecycle events and then trigger those lifecycle events and the callbacks that are associated with them at the right point. But still, this thing will allow you to not have those pieces of code within your training loop, but they will be factored out and interchangeable to some degree, which is an advantage in the trainer. So kind of Fabric loves the Lightning module. So this is an example of a Lightning module. You have a training step, a configure optimizers, the data loader, and so on. And then what you can do with Fabric is you will create a Fabric object, and then you will get the optimizers from the model by calling configure optimizers manually. You remember the anatomy of the fit method. Here it's kind of unbundled. And for some time internally, we called Fabric Lightning Unbundled for this reason. We're kind of turning the trainer upside down and say, okay, if you want to use pieces of it, just in raw code or to create your own trainer, now you can do it. And this is an example of that. You set up your model optimizer, you set up your train data loaders, and then you call the hooks at the right time. So on train start, you notify essentially Fabric that training is starting, you train, and then you call Fabric backward just in the raw Fabric way. But then if a condition is verified in the last line, you can call another hook before we called on train start, which kind of executed the code that the user implemented for on train start, and then you could call it whatever other lifecycle hook in the model. And so this code is kind of model independent because it doesn't contain any model specific code, but it's still something while being fully decoupled. So you could replace one model with another model that exposes kind of the same lifecycle hooks. You could still be in full control of what this training loop does. And so, for example, if you need to access things like reinforcement learning or active learning, things that required heavy customization of how the trainer worked. We had in the trainer we had an extensible architecture for loops, but that required you to understand how the trainer worked internally, which is something we cannot ask our users beyond a certain point. I think that if you want to use a trainer because you're happy with a usual functionality of the trainer, that's fine. Otherwise, you should look into Fabric to say, okay, I have a reinforcement learning problem, and I want my agents to be organized in a certain way and to interact with the environment and so on. And you have full control of that, but you can still then use the Fabric facilities to remove the boilerplate from your code. And eventually even use a Lightning module to do that. Okay, so now we have another data point, Fabric plus Lightning module in the spectrum between full control and full management. I mentioned callbacks before. Yes, you can pass callbacks to Fabric again, and then you will have to manually then trigger the same event that the callback will react to, and then pass arguments to it. And this is a very simple mechanism, but it's actually quite effective to make you kind of manage a complex model code base, something that needs to scale up as well. And this is an example of using multiple callbacks. All right, so we have a last data point where you have all the ingredients that would allow you to build your own trainer model after the PyTorch Lightning trainer, but that could be verticalized on a specific application. So right now, basically, the risk of buying into Lightning 100% and that we understood could be associated to some pain if you go to certain kinds of problem, like reinforcement learning, or certain kinds of skills that we still allow you to scale a lot through deep speed and the other strategies, but for specific problems, then you start like needing to tweak the trainer. This is what you can access at this point. And so you can go anywhere in the spectrum and kind of trace your own path to it. There's another aspect I want to touch briefly upon, which is the communication primitives. If we look into code like Megatron, highly optimized code implementing different kinds of parallelism, Megatron LM has been used in multiple projects like Big Science, Bloom, GPT Neo X from Euler AI, and so on. So these collectives have kind of cloned the Megatron repo. They put deep speed on top of it. And but if you look at the Megatron code, it contains the management, for example, of parallel groups based on global variables and so on. And if you know what you're doing, that this makes perfect sense. But this is a big barrier for practitioners to deal with and modify and experiment. So what we try to do with Fabric is in this process of unbundling the functionalities that make PyTorch Lightning great, we want to bring in some of the primitives that will allow you to use those primitives directly in your models, even in the layers, if it's tensor parallelism, or somewhere else in your train loop, if it's other type of parallelism, but still be somewhat abstracted away with some information. For example, these globals that you see here, handled by the Fabric object directly. So you don't have to mess with those. And it's not just convenience. It's that if you are not in full control of something so complex, this is where bugs will happen. So it's much better if you don't have to deal with this 100%. And we all know that bugs in machine learning and deep learning, even worse, and foundation model even worse, are really hard to spot. And probably most of the times you will find out about them way too late. So the less surface for error, the better it is for everyone. So the communication API for Fabric looks a bit like this. We have a launcher. You pass the number of devices, number of nodes that Fabric will run on. And then the launcher will set up the different processes in a way that is consistent in terms of what is the word size, what is the global rank of the process, the local rank on the local node, and then the node rank itself. And so then you can write code that, for example, executes something on a single rank. And will be extending this with the possibility of creating multiple groups. And so you can manage different process groups that do different things in a way that is like ergonomic through the Fabric object. And we are also exposing communication APIs that are abstract with respect to the backend you use. And sometimes these things kind of interact with the strategies. So you will end up, if you don't use this, you will end up using a certain strategy and kind of overfit your code to that strategy. So it's kind of, there's some impedance going to and try something else and see if it's better or not, because you will need to modify your code. What we want to avoid It's precisely this effect. So we're introducing things like fabric.barrier, broadcast, gather, reduce, all these operations that will be called this way. As you can see, fabric.barrier, fabric.broadcast with a number in this case, or all gather for data, and all reduce. So you will be able to sum, for example, or average throughout a set of machines, and the actual backend that this will execute on is something you decide when you instantiate the Fabric object. So again, your code won't change, and you can kind of have full control of what this will run on based on how you initialize the Fabric object. But your code will stay the same. So even if you use a call to Fabric broadcast within a layer, then that will play nicely with the rest of your code base based on how the Fabric object will be initialized. Of course, you need to pass the Fabric object through, but this is not a big deal. It's something that is idiomatic. All right. So as you've seen, we're evolving PyTorch Lightning to accommodate the new era of foundation models. Although PyTorch Lightning has been used for some of them, we want something that can address also the pains that we've heard from some applications. Where I mentioned reinforcement learning was one of them, and some language models were that very big models like people using Megatron and so on. We also heard about some pain points, and we believe we introduced something that can surpass whatever PyTorch Lightning was offering by a significant amount. And so this is why we decided to cut the Lightning 2.0 release, and it's coming in a month. And I want to go through some of the things that we'll have in there. Essentially, PyTorch Lightning will have a new trainer, which is almost fully compatible with the previous one. And by the way, the 1.9x will be supported in the long term. But I'll tell you in a second what we're doing with the trainer. And it goes in the direction of making people more productive. And so I'll explain you in a second what it does. And then there's Fabric, which in time, you see that dotted, that dashed thing between the two boxes, will power more and more of the trainer. So right now, some of the functionality will be duplicated, but it's not a problem. Like it's not a user-facing change, and in time we'll be replacing some internals of the trainer with internals of Fabric, because basically that's a natural evolution. And of course, we have apps that are not in scope for this talk, but that I'm encouraging you to check out at lightning.ai. And so what is Lightning Trainer 2.0? Lightning Trainer 2.0 is a tighter trainer. It will have fewer abstractions. So if you ever try to step into the trainer, you go down with a lot of levels. And this has been a source of complaint, because if you have a complicated problem to solve and you hit a bug and you want to step through what the trainer is doing, with the current trainer, you need to know what is what, and you spend time kind of trying to understand what the trainer is doing. Not because it's inefficient is what it's doing, because most of the functionalities that are interspersed in there are really functionalities that are deactivated if you're not using them. So they don't have a performance implication, but for sure they have some kind of code inspection implication. And so developer friendliness in general. So we're removing quite a few dependencies. We're tightening up the abstractions. And thanks to Fabric being there, we're also removing certain functionalities that were kind of complicating the trainer itself. So you will see with Trainer 2.0, a tighter trainer, easier to work with, easier to inspect. We're also making the API for the trainer and Lightning module as stable as possible. So we were through the 1.0x series. There were some API changes. We heard a few people complaining about the certain options for the trainer changing or a name for hook changing. In fact, we go through a very rigorous deprecation process that takes deprecation through 2 or 3 releases. The point is that many people are just using the PyTorch Lightning as a certain release, and then where they are not updating it for a long time, and so they will hit when they try to upgrade, they will hit a time where all the deprecation process has gone, essentially. And so they lose that. So one thing we're doing is we are turning warnings, deprecation warnings, into errors. So you have visibility on what changed and why. But with a Trainer 2.0, we want to make that API as stable as possible because we had the time to kind of perfect it in the 1.x series. So we're making the commitment of like making sure that we won't be changing the API as much as possible. We're doing things more opt-in and less opt-out. We are taking this opportunity to say, okay, if there's some functionality that is convenient, users have the visibility, they can discover it, but if it has any performance implication or something, then we'll make it opt-in so that you will get a perfect experience out of the box, but and you can still discover other things you can do, but we won't try to do it for you too much. And then we're introducing Fabric, with which you can get full control. And then we are, of course, getting up to speed to full PyTorch 2.0 support. A few of these things are already present in the 1.9 release. For example, Fabric is already out in beta. You can try it out. And PyTorch 2.0 support is already there. But we're, of course, intensifying testing and so on so that we can be fully aligned by the time we release mid-March. Okay, so with this, I hope you enjoyed the evolution of PyTorch Lightning, and please reach out to us. We have a very lively Slack. We have forums. Please visit the forums. We kind of revived the forums. There was a lot of requests for that. We're very active on GitHub, and please check out the Twitter handle as well if you want. And with this, I would like to thank the developers that work on a daily basis on PyTorch Lightning and Fabric, and that interact with the community, help them out on Slack, on the forums, and hear the pains and try to make the experience as good as it can get. We are very community facing in the sense that we take whatever inputs comes from our users very seriously, and many of the developers that are named here were a part of the community at the beginning of their journey, and they're now working with us on a daily basis. I also want to mention the Lightning League, which is a group of developers that take Lightning at heart and want to contribute and kind of help others jump on board and build new interesting things that are willing to show to the community as well. So with this, I would like to kind of open up for questions, reach out to us on the forums and on Slack. And thanks a lot.